Hello everyone, today we're going to be going over the answers to the examples for the molecular geometry questions. So it says to determine the electron domain geometry and molecular geometry of the following molecules. So we'll start with BF3. In order to determine both of these geometries, we have to first draw the structure. So, as you know, for Lewis structures, we're going to determine the number of valence electrons. So boron has 3 valence electrons, fluorine has 7 times 3. So that gives us a total of 24 electrons. So now when we draw the Lewis structure for this, we're going to put boron in the middle because it's the least electronegative, and we're going to surround it by our fluorines. And then we're going to connect them all by single bonds. So that used up 6 of our electrons, 2 from each bond. So now we have 18 remaining. So what we're going to do is we're going to add 3 lone pairs around each fluorine to give it a full octet. And that used up all of our remaining 18 electrons. So now we have our Lewis structure, and here we can note that the boron is an exception because it does not have a full octet. But that ends up working out because we have learned our exceptions. So now we can say that there are 3 total electron groups surrounding that boron, but there's 0 lone pairs. And recall, electron domain geometry is the total number of electron groups surrounding that central atom, whereas molecular geometry takes into consideration the number of lone pairs because of that repulsion that is caused by it. So for electron domain geometry, we're going to just look at 3 total electron groups. So that will be our trigonal planar. And then since we have 0 lone pairs, right there, our molecular geometry will be the same. So it's also that trigonal planar. Now let's move on to XeF4, xenon fluorine. So looking at the periodic table, we know xenon has 8 valence electrons, and fluorine, like we just said, has 7 times 4. So that gives us a total of 36 electrons. So we're going to put xenon in the middle because it's the least electronegative and surround it with single bonded fluorines. So that used up 8 of our electrons, 2 from each bond. So now we have 28 remaining. I'm going to add that up here. It's 28 remaining. And so then, like we did last time, we're going to add lone pairs around each fluorine. And so we added essentially 6 electrons around each fluorine. So 6 times 4 is 24. So now we have 4 electrons remaining. So where do these 4 electrons go, you might ask? Well, xenon is a atom that can have an expanded octet. So we're going to go ahead and put those two lone pairs on the xenon. And we're going to note that it has expanded octet. And then in regards to our electron groups, we have to count those lone pairs. So there are a total of 6 electron groups, 4 bonds, and 2 lone pairs. So that means our electron domain geometry is the total number of electron groups. So we have 6 here, so that's going to be our octahedral. And then our molecular geometry, we have to consider the lone pairs. So we have 6 electron groups and 2 lone pairs. So that leaves us with a square planar geometry. All right, number 3, SO3 2-. So remember with this 2-, we have to consider this charge as 2 extra electrons that we add on to the total number of valence electrons. So sulfur has 6 valence electrons, and oxygen also has 6 times 3. And then we got to add the 2 to that total. So we have 6 times 3, 18, plus 2 plus 6. We have a total of 26 valence electrons. So let's put sulfur in the middle, surrounded by our oxygens. And for now, let's just add single bonds in between each oxygen. So that used up 6 electrons. Now we have 20 remaining. So we can go ahead and add lone pairs around each oxygen. So that used up 18, 6 around each oxygen. And so now we have 2 electrons left, so we can put them there. But let's take a look at our formal charges. Recall, formal charge is the number of valence electrons minus non-bonding minus 1/2 bonding electrons. So for our sulfur has 6 valence electrons, minus those 2 from the lone pair, minus 1/2 of 2, 4, 6, those 3 bonds that surround it. So that leaves us with a +1 charge. Now if we look at all of our oxygens, all the oxygens are the same in this case. It has 6 valence electrons. It has 6 from the non-bonding, 3 lone pairs times 2 each, minus 1/2 of 2, leaves us with a -1 charge. So right now we have +1 on sulfur and -1 on each of these oxygens. Let's see if we can make this a better structure by reducing our formal charges. So I'm going to go ahead and erase all this, and then I'm just going to pick out this oxygen right here that we're going to adjust. So if we go ahead and add a double bond here, taking one of those lone pairs and putting it up there, let's see what that does to our formal charges. So formal charge of sulfur still has 6 valence electrons, still has 2 from the non-bonding, but now it has 1/2 of 8 because we have 4 total bonds. We have this one, this one, this one, and this one. So that leaves us with a 0 overall charge. Now these 2 oxygens right here are still the same, so they're still -1. But this one down here, let's take a look at. 6 valence electrons minus now only 4 from the non-bonding, and then 1/2 of 4 from the bonding right here. So that also leaves with a 0 overall charge. So this is now our better structure because we have reduced the formal charges and we still have that overall charge of -2 because we have this -1 and this -1. So now let's look at the total number of electron groups surrounding the sulfur. We got 1, 2, 3, 4 total electron groups with 1 lone pair. So that means our electron domain geometry for total electron groups is right here. So that means we have a tetrahedral. And then our molecular geometry we consider that lone pair. So we have 1 lone pair, 4 electron groups. That leaves us with trigonal pyramid. Okay, number 4, carbon dioxide. Same thing, we'll do carbon has 4 valence electrons, oxygen has 6 times 2, and that gives us a total of 16 electrons. So we'll put carbon in the middle and surrounded by our oxygens. And we'll add single bonds for now, so that takes away 4 electrons, 2 from each bond. So we have 12 remaining. So if we go ahead and add our lone pairs around here that used up all 12 of them, but we can see that this carbon now does not have nearly a full octet, and these oxygens, like in our last case, will have a formal charge of -1. So let's see what we can do. We can take away each of those lone pairs and put them here as double bonds so that now our carbon has a full octet and everything is happy. So now we have 2 electron groups, right? Because these lone pairs are each counted as 1 electron group each, and we have 0 lone pairs on that carbon. So our electron domain geometry is right here with 2 electron groups, linear. And then our molecular geometry since we have 0 lone pairs, it's the same as our electron domain geometry. All right, last one, SF4. Like we've done before, sulfur has 6 valence electrons and fluorine has 7 times 4. That gives us a total of 34 electrons. So we'll put sulfur in the middle, surround it by our fluorines, and give it single bonds all around. So that used up 8 electrons. We have 26 remaining. And once again, we'll give the fluorines a full octet to make it happy. So that used a total of 6 surrounding each fluorine, so 6 times 4 is 24. So now we have 2 remaining. Where do we put these 2? Remember, sulfur is one of those elements that can have an expanded octet, so we're going to go ahead and put them on that sulfur. And I'll note that it has an expanded octet. This also makes sense because if we did the formal charge of our sulfur, remember it has 6 valence electrons, 2 from the non-bonding here, and then 1/2 of 2, 4, 6, 8. So that leaves us with an overall charge of 0, and these fluorines are also 0. So the overall charge of this molecule is 0, which we want. Now let's look at the total number of electron groups. We have 4 bonds and 1 lone pair, so that's 5 total electron groups. And 1 is a lone pair. So that means our electron domain geometry is our 5 total electron groups, so that's a trigonal bipyramid. And then our molecular geometry we take into consideration that lone pair, 1 lone pair, 5 electron groups. We have a seesaw. All right, that's it for the practice problems on molecular geometry. Thanks for watching.